recording. I've had interesting luck of late. It looks like it's recording. So we are starting with electrostatics.
When do we get to see this?
Huh? Do what? Do what?
Never mind, it was answered.
It's okay. Yeah, I will get you the test on Monday. Or you can stop by my office early Monday morning and pick it up if you want. And we'll dig into it. Because I finally got everything graded after they locked up the building, so I couldn't get them to Mr. Ken to be able to pass them out. But I did manage to ultimately get everything graded and get it going. All right, so we've been talking about electrostatics, or started talking about electrostatics. I have a positive charge, and Ben Franklin got it wrong. The proton carries a positive charge, and my electron carries my negative charge. And in my positive charge and my negative charge, the proton also has more mass. The mass of the proton is much, much greater than the mass of the electron. If I remember right, this is times 10 to the minus 31, and this is like 10 to the minus 23. So the masses are very, very different. And hot off the press, as of September 6th, this is the current accepted radius of a proton. Anybody know what femto is? Anybody got a guess at what femto is?
Times 10 to the negative
19, and that's better. It's 10 to the minus 15. And actually there's a controversy. Apparently there are two ways of measuring the radius of a proton. This way is the one that the high energy physicists want. And there's another one that actually says that the proton is bigger. And it's actually, the measurements are falling into two camps. This camp or the bigger camp, and I think it depends on the situation that the proton is in order for the measurement to be there, and we're about to talk about why that might be the case. But this result was announced in the journal Science on September the 6th. So that news is hot off the press. Hot off the press. So that's the current radius of a proton. Big thing is that my charge on a proton or my charge on an electron is going to be 1.6 times 10 to the minus 19 coulombs. And we usually carry that out. It's like 1.602 times 10 to the minus 19 coulombs. And you usually worry about it if you're worrying about significant figures to the 3 significant figures. So that 1.60 times 10 to the minus 19 is my standard charge. Okay, that's my standard charge. So one electron is going to have a charge of minus 1.60 times 10 to the minus 19. My one standard proton is going to have a charge of 1.6 times 10 to the minus 19. And by the end of the semester, you will have this number ingrained in your head. The other thing that we need is K, and this is not a spring constant K. I know that's going to make everything crazy right now. It's not a spring constant K. This is Coulomb's constant, and Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared coulombs squared. And most of the time, you can get away with just doing 9 times 10 to the 9th Newton meters squared, coulombs squared. And just as a reminder, because we've been doing this for a while, and it's been, if I have 10 to the 11th, some number, we'll call it 1.2 times 10 to the 11th, and I'm multiplying some number like 3.4 times 10 to the 12th, I'm going to have 1.2 times 3.4 times 10, the 11th, you add the 12, that becomes 23, 10 to the 23rd. So just as a reminder how to work with exponents, because that's going to help you out a lot when you're trying to multiply stuff into your calculator. Even though the calculator will work well with the exponents, this is just going to help you out a bit. And if I did 1.2 times 10 to the 11th divided by 3.4 times 10 to the minus, or 10 to the 12th, that's going to be 1.2 divided by 3.4 times 10, 11 minus 12, which is going to give me just 1. So I'm going to get 1.2 divided by 3.4 times 10 to the minus 1. And it's going to help you out as we start working with these equations, and we're working with different things. So if you want to review, you can. It's in the appendix of your book. But because we're going to be dealing with a lot of times 10 to the minus 19s and times 10 to the minus 9s, at least for the next couple of weeks. Or 10 to the plus 9s for at least a couple of weeks. So that's just something you might want to go back and look at and review. So let's take the force due to gravity. So I've got the Earth here. And in Physics 1, we talk about contact forces, and we talk about field forces. Okay? So we can classify forces into 2 different ways. Now, if I have Earth, we know that the acceleration due to gravity is going to go down towards the center of the Earth. And we know that if I put a ball here, it's going to be drawn towards the center of the Earth. So if I write Newton's universal law of gravitation, we know it's a vector, and that's our g, mass 1, mass 2, divided by r12 squared. And its vector component is a unit vector in the r direction. So if I'm looking at this as a vector, I'm going to be in the unit r direction associated with that particular component. Now, again, this is the problem. Ben Franklin got it wrong, and we have a proton, and we're going to use a test proton a lot as we start moving forward. So we're going to be looking at the behavior of the proton. Now, our test charge proton, we're also going to make, when we do a test charge, we're also going to assume it doesn't have any mass, and we're about to show you why we're going to make that assumption, and we're not going to be worried about it. Okay, we're going to be able to make that assumption and not be worried about it. But Ben Franklin chose to give us the direction like this. So if I'm looking at that field around my proton, I'm going out from the proton. So it's a little opposite what we do with our gravitational, but I can get a field, and this is going to be that electric field, and everybody's measured electric fields, sort of. you actually measured equal potential, and we'll get there, but I'm going to be looking at the positive. And if I look at the negative, I'm going to have it going into the negative. Okay? So if I'm looking at the field that's being generated by the proton, it's going to be looking at it going outward. And if I look at the field associated with the electron, it's going to be looking at it going inward. Now, if I take that test charge, so here's my little test charge, right? The reason we get that direction is because if I have a test charge, guess what? It's going to want to move away from my proton. And if I've made the assumption that my test charge is positive, it's going to want to move away from my proton. If I make the assumption that my test charge is negative or positive, it's going to move towards the electron. So that's why we get the field lines drawn the way they do. That's why we get the field lines drawn the way they are. Now, even though we haven't done it, but I know you guys are going to be working on, okay, I'm going to be positive and know you guys are going to be working on your laboratory reports for next week over the weekend, right? Most likely it'll be Tuesday, right? For you guys, it'll be Tuesday. Most likely it'll be Thursday for you guys, right? I know, you know, we're all being honest, right? All being honest. But if I look at the one that's like this, right, and I want to draw my electric field, think about what you know because you've played with it. We've all played with it. If I have a north and south magnet, because we've all played with the toy that has the iron filings in it, and you've been able to put the little magnets around, and you've been able to do it. We know because the iron filings are going to line up along those field lines. And this would be, and we'll get there eventually, this is going to be my magnetic field, right? I'll get lines that look like that. Well, I'm going to get the same thing with these. I'm going to get my electric field. And in this case, we can actually draw the direction of our field lines. Okay? But what you measured in the lab was a little different. So let's go back to Earth here. And if I think about my potential energy, right, I could draw a circle around the Earth that has equal potential energy. And I know that if I go further out, it has equal potential energy further out, right? And these things are right angles to each other. So these are called lines of equal potential. And that's actually what you measured in the lab. So if I do that here, I'm going to get lines of equal potential around my charges. Okay? And my field lines we can infer because we can do them as 90-degree angles. Now, if I look at this, and then I look at those straight line ones, just think that I have a series of point charges along those lines, and what that's going to ultimately do, and when you measured equal potential lines, at least for this one, you got nice straight lines like this, because those two parallel lines are going to give you an area of uniform field. And if this is your positive side and this is your negative side, you're going to get nice uniform lines that look like that. And I can actually generate a uniform electric field between two parallel lines. And we're going to see that that actually becomes our first electronic device. Kayla, you're catching. And you're over there, and I'm sneezing over here. You're catching. All right. Yeah.
What are those lines called again? Lines of equal...
Equal potential. Equal potential. And for those of you who may want to read on so that you get a better lab report, this is going to be V. Okay? We're going to use V as potential, and it's going to turn out that V is a scalar, which is going to make our lives really, really easy, because it's going to do the same thing that we did back in mechanics. And one of the things for you guys is that some of you are going to get this stuff better than you did in mechanics, and vice versa. For some of you, you're going to have to make the parallels between mechanics and electromagnetics. But for some of you, you're going to go, well, why didn't you tell me that in the first place? Because it makes so much more sense in electromagnetics. And it's how your brain is wired. It truly is how your brain is wired. You may be thinking it more from this perspective and have to make the parallels back to mechanics, or vice versa. So that's one of the weirdnesses of why do we make you take physics 1 before making you take physics 2? Because there is a school of thought out there that physics 2 may be a little easier for some people to grasp, and they should take physics 2 first and then go back and take physics 1. But traditionally, we start with the mechanics side and come over. And you guys are going to see that from a calculus perspective in a little while. Okay? Because most of calculus actually was derived trying to explain electromagnetic fields. Other than Newton's sums and doing that integration and derivative part, most of calculus comes in trying to explain what we're drawing here, or what's happening when I have a conducting surface and what's happening on the inside of a conducting surface. So we're actually going to see more of the mathematics come in and ultimately you're going to get a history lesson in both math and science, because we start electrostatics and magnetics doing just observations. And Faraday, everybody knows Faraday, right? We've all known Faraday. Faraday was a crap mathematician. He didn't do any mathematics. He just did experiments. And he had a mathematician try to figure out what it was he was doing. And then you had some mathematicians that were going, well, the mathematics would say this. And then somebody like Faraday or Gauss, and Gauss was both a mathematician and an experimentalist, you'd have people be able to say, oh, that's what's happening. So electromagnetics and calculus kind of grow up together. They definitely grow up together. And we're going to see that. And just like back in mechanics, we were dealing with forces that had a vector component to it. And we were trying to solve problems using forces, and that got to be a real pain in the tushy. And then we got to go to work and energy, and all of a sudden I didn't have to worry anymore about direction. I didn't have to worry, I lost that directionality, and I could say, well, the energy at the top's got to equal the energy at the bottom, and I can work the problem that way. And the same thing is going to happen here, and we're going to get something that's called V for potential. And we're very familiar with V for potential from something else, volt. And electrical potential is going to be kind of an energy, and we're going to talk about it, but we have to do some little twists associated with it. But my other one that we're going to get is we're going to get my electric field is going to be the big capital letter E, and it's going to have directionality. And then, but we start with F, which is our force. And we'll get to E probably by Friday of next week. Actually, we may get to E by Wednesday. I'm not 100% sure. But when you're dealing, so what this is it's saying I'm getting these as equal potential here. and I'm going to be able to infer the direction of my electric field. In magnets, we can actually put iron on there and get something responsive, and we can see it. And we can see it really well. We don't even have to do this. We could actually use compasses, you know, a little compass, and actually do it. So when we do magnetic fields, magnetic fields are a lot easier to see. Electric fields, we really can't measure, but we can measure potential. So we can go back and forth to look at that. All right, so we're going to go back to why the mass doesn't matter. So we have two force equations right now. We have the force that's the Coulomb force, which has got a K, a charge squared, and it's into that. Go back here for a second. Okay. Now, your text is actually going to put in a negative. But I'm not going to worry about a positive or negative because it's all about which way I'm dealing with the R. Okay? It's all about which way I'm dealing with the R. And I may end up bringing it out or because we're going to end up dealing with the magnitude and looking at the direction. But the other one is, and this is also going to be highly dependent on if this one's positive and this one's negative, and I'm looking at this force on that side, that negative comes into play. So a lot of times you don't even see that negative. We end up conceptually talking about it. The same with this one. It's also dependent on which one is the bigger mass, right? The bigger mass is going to have the better attraction. So these two right here, I'm going to clean it up because I'm going to make a couple points here. This is a unit vector in the same direction as the distance between the 2 points. The same holds true for my gravitational. Okay? The form of these equations is the same. I've got a constant. In this case, I have two charges. In this case, I have two masses. The form is the same. And the force goes as 1 over r squared. Okay, the force goes as 1 over r squared. So you can start looking at a lot of parallels that happen that start making a little bit more sense. So you can actually look at it from that perspective. Now, charge, going back to our charge, going back to my charge page here. These are quantized. 1 electron is 1.6 times 10 to the minus 19 coulombs. 2 electrons would be 2 times that. 3 electrons would be 3 times that. Same with protons. This is quantized, and we've measured it by the Millikan oil drop experiment, and we know what that is. So we know what that charge is. So let's do this. All right. We're going to look at the gravitational force versus the electric force between a proton and an electron in the hydrogen atom. Okay? We're going to look at the two forces in the hydrogen atom. So I'm going to do it a little differently. So I'm going to have force times r squared. This is going to be K, Q, Q. And the force times r squared is going to be G, M, M. Because this r and that r are the same, right? So I don't have to worry too much about that. The difference then on this side is going to be related to the magnitude of the force. So let's take my K. My K is going to be, if I go back and look at it, I'm going to go ahead and use 9 times 10 to the 9th. And most of the time, if you use 9 times 10 to the 9th, Webb sign is going to be okay. There may be some where you have to go back and use the 8.99. This is Newton meters squared, coulombs squared. So I'm going to have F r squared is equal to 9 times 10 to the 9th, 1.6 times 10 to the minus 19. And this is a minus 1.6 times 10 to the minus 19. But if we're only worried about magnitude, I don't have to worry about that negative. So I get 1.6, let's go there. 9 times 1.6 times 1.6 gives me 23.04, and I get 10. 9 minus 19 minus 19 gives me to the minus 29. All right, now if I do the other one, G is 6.67 times 10 to the minus 11 Newton meters squared, kilograms squared. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So I take my 6.67 plus, oh, I don't want to add it, 6.67 times 1.67 times 9.11 gives me 101 times 10 minus 11 minus 27 minus 31. So I get 101 times 10 to the negative 59. That's 29, that's 59, 30 orders of magnitude different. The electron does not care about the gravitational force between it and the proton. It's not even going to worry about it. Not going to be an issue. So when I do this test charge thing, I don't have to worry about the gravitational force. It's not going to happen. Right? Not happening whatsoever. Electrostatics? Oh, you betcha. My electrostatics are going to be a big deal. And charge is huge. And we know that because I get ionic crystals, right? We get sodium chloride salt crystals are all based on the attractions of that sodium and that chlorine. One's positive, one's negative, and they're going to pack because that electrostatic force, there's this one, that electrostatic force is a big deal. And it's orders of magnitude different than this. This is times, the constant's times 10 to the 9th. The constant here is times 10 to the minus 11. Now, if I got big, huge masses, that's a different story, right? That's a totally different story, but I don't. So I get the fact that I can, and so now, when we start talking about placing a test charge in here, you can understand that I only have to worry about the charge, I don't have to worry about the mass. It's not going to come into play. It's not going to come into play at all. Got any questions over there? Okay, so let's do one. I'm going to keep my numbers here accessible. Okay. So, I'm going to have a positive charge. Okay, I'm going to have a positive charge. And you're going to see that we're going to use, to make life easier on us, 1 coulomb of charge is actually a lot of charge. So we're going to do this as 3 nanocoulombs. So this charge is going to be 3 nanocoulombs. I'm going to have a negative charge of 5 nanocoulombs. And we're going to keep this at a distance of 0.5 meters. Then I've got another one that's a negative charge, and it's going to be 1 nanocoulomb. And it's going to be at a distance of 0.75 meters. I want to find the net force on that charge. And that's the tricky part, okay? When you start working these problems, you've got to know which charge you're looking at and keeping track of which charge. So the way you kind of approach it is I start out by finding the magnitude. So I'm going to find the magnitude of the force on between these 2 charges. Okay? So I've got my 9 times 10 to the 9th Newton meters squared coulombs squared. I've got my 3 times 10 to the minus 9 because that's nanocoulombs. I have my 5 times 10 to the minus 9 nanocoulombs divided by my 0.5 meters squared. So this is coulombs, that's coulombs, coulombs cancel, meters squared cancel, and I end up with that. So I'm going to get 9 times 3 times 5 gives me 135 divided by 0.5 squared. That's going to be 0.25, and this is going to be times 10 to the 9 minus 9 minus 9. Those cancel out, so I'm to the minus 9. That makes life nice. And this becomes 540 times 10 to the minus 9. And that's in newtons. I'm going to do the magnitude of the force, 5 and 1. So I'm going to get my 9 times 10 to the 9th. I'm going to have my 5 times 10 to the minus 9. I'm going to have my 1 times 10 to the minus 9 divided by my 0.75 squared. So I'm going to have 40, that'll be 45, right? So that's 45.75 squared. Oops. 0.75 squared. This is 0.5625, and this is times 10 to the minus 9, because those cancel and I get a 10 to the minus 9. So this gives me 45 divided by 0.5625. This gives me 80 times 10 to the minus 9. So I've got 80 times 10 to the minus 9. I have 540 times 10 to the minus 9. Now I got to do my sum of my forces. So this is a positive, this is a negative. So this charge is going to want to go this direction based on the fact that this is an attractive force. So that's my force, 3, 5. Now this one, it's going to want to move away from that one. So this is force 5, 1. So if I'm doing the sum of the forces, this is going to end up being negative because it's going that direction, both of them. And I'm going to have my 540 times 10 to the minus 9 plus my 80 times 10 to the minus 9. And now we know the answer is going to end up by 10 to the minus 9, right? And so my 540 plus 80 is going to give me 620 going that direction newtons. And if I didn't have a calculator, you see now why dealing with my exponents really helps me out, because a lot of us could do some of these calculations in our head, and I don't even need a scientific calculator in order to do it. The next thing we do is we take it out of one dimension. We take it out of one dimension. I only got 4 minutes, so let's set one up. So I've got a positive charge, and we'll go ahead and do 3 nanocoulombs. I've got a negative charge of 2 nanocoulombs. And I'm going to do a positive charge of 1 nanocoulomb. And we're going to say that this is 0.1 meters. And this is 0.2 meters. And we want to know the force on that charge. Okay, we want to know the force on that charge. So what we're going to end up doing is we're going to calculate the force 3,2. And we know what that's going to do, right? That's going to go there. And we're going to calculate the force 1, 2, and we know that this is going to go there. We're going to get a force vector that's going to have the negative, because this is going to be going down, or this is going to be positive. I was doing it backwards. This is going to be F32 in the I direction minus F12 in the J direction. Then you can calculate the magnitude, and then you can calculate the angle. So it gets it set up for you to start playing with it so you can start playing with the homework. So you guys good? No? Takes practice. It's just practice. Just practice. Just practice. But hopefully it helps with your lab. Hopefully it helps with a few other things. And I'll be in my office on Monday.